Hello YouTube viewers, welcome to my show Science Thursday. In today's episode, I'm going to talk about a very requested topic, jet engine. So let's dive right into it. Well, you have to understand, jet engine is a very big topic. It's like almost a rocket system itself. So I'm gonna make multiple videos after this video, but this video is more as a guide, as a like, okay, this is what we are talking about. So you can understand when I cover a ramjet, scramjet, you can understand them much more thoroughly. So this will not be a quote unquote complete. But again, it cannot be complete. You have to do engineering for 4 or 5 years before you can understand that. So this is just an introduction. What the hell is going on? So we are talking about something that takes chemical energy and turns it into physical thrust. Now this is the main difference between your internal combustion engine that is in your car versus a jet engine. Jet engine takes that basically chemical energy and converts into hot jet exhaust. That's all it's doing, is basically taking it and quote unquote using a burner and turning it into a blowtorch. However, the blowtorch, while it does have high temperature, it does not have high exhaust velocity. Basically the gas that is coming out is not that fast. It's not going at like Mach 3 or Mach 4. Basically it does not have the oomph necessary to push a plane. So that's what you're doing. You're taking the chemical energy in your fuel, generally kerosene, very refined kerosene, which is classified as jet propellant 1, and military have different techniques. Basically they make sure they remove water or any moisture from the kerosene, because planes go very high altitude and it can go very cold at that time, and if something freezes up in the wrong place, let's say fuel pump or the inlet to the fuel, yeah, you're gonna fall from the sky. So they make sure that kerosene is up to the quality. So you take the fuel, again generally a hydrocarbon, generally in format of kerosene, and then you mix atmospheric oxygen. Now this is one core difference between rockets and jet engine, because if you study jet engines, like you're curious about it and you're googling them, you will always see units that are used for rockets, because they'll say, oh, this has like 500 kilonewtons of thrust, and then again you study about a Raptor engine or Merlin engine, they're like, again the units may be a bit larger. They might have like, this has 2000 kilonewton, but again kilonewtons also, this also used kilonewton. Why? Because it has physical thrust, not rotation. It's not creating torque, it's creating thrust. Basically it's taking action equals reaction principle to the basic. That's it. Like you are throwing things at your back, so you get pushed forward. So jet engine pushes things at the back and gets pushed forward. Action equals reaction. And that is the reason why rocket can work in space, because it carries its own oxygen, rocket carries its own oxygen, and it's not reacting to anything. Jet engine, basically a plane is reacting to the atmosphere, otherwise it will simply not work. However, rocket is independent. So that's what you're talking about. Now jet engine is like a diesel engine. Like you're not gonna build a diesel engine for your moped or tiny scooty, because it's not efficient enough at those scales. But if you're talking about, hey, I'm gonna move a locomotive, or I'm gonna have like hundreds of tons of cargo, yeah, petrol is not suited for that. You have to go to diesel engine. Same for these things. These things are big. Basically the bigger you make them, more efficient they get. So if you are moving 200-ton space shuttle, these puppies are like, I got this. But if you put them in a motorbike, they're like, dude, why? Like you can do that, somebody did that, but again it's not appropriate use of that. Now the sole reason why you see them so much in aircraft industry is because they have one of the highest power to weight ratio. Basically if they have a size, basically let's say this is the size and this is the weight of it, let's say 1 ton, and how much energy you can get out of that 1 ton, it's very high. Let's say it's 10 megawatt, but for a petrol engine comparatively it would be barely few megawatts, barely 2-3 megawatts. Diesel 4 or 5. This puppy would be like 10-20. So that is the reality of it. Like given the size, given the weight of it, it is ludicrously powerful. Like a small jet engine can do a lot. Like that's why fighter jets are like capable of going to a Mach 2. It has a lot of oomph for its size. So this is one what we call like don't judge it by size. Basically this is what thing is. So let's talk about this working. What the hell it's doing? It's doing something very simple. It's taking air from the atmosphere. You have to understand that it does not have its own oxygen, so it takes air from the atmosphere. Now it compresses it for optimal burn. Now this would be a very tricky thing. Generally you want a smooth, calm, or even cold airflow. Heck, you have a turbocharger diesel vehicle or a turbocharger petrol, they might even have inner coolers to cool the air. You want compressed air, so it's higher density, but you don't want it hot. So but if you are doing it so continuously, it will get hot. So why the hell we want compress in the first place? Because air, let's say 1 liter has 1 liter of air into it. That translates to some amount of oxygen. Now some amount of oxygen, let's say you burnt at 100% efficiency, converted that burnt energy into useful thrust 100% efficiency, which cannot be done. But let's say you did that, but that will give you still a very large vacancy. Basically your plane, let's say it's 200 tons, it needs more than few milligrams of petrol. It needs like at least 2-3 liters per minute in order to get enough energy that in principle it should move. So you can realize that engineers have to design this puppy so it can burn at least 10-20 liters. If it needs 1 or 2, they will burn it 10-20, so at least it get the initial inertia going, and then they will throttle it down once it in the cruising altitude. So you need that kind of power. Now if you put that much fuel in anything, you're just gonna choke it. It's simply not gonna burn because there is not enough oxygen. For that reason compressors work. That was why you have to put so much air into it so you can burn that amount of fuel. You have to compress it, and you have to compress it by a lot, and I will explain that further. So burning happens in very high temperature and pressure. So that's what you're getting the air, then you're getting compressing it. So at the point of combustion, you're getting a lot of chemical energy into a lot of air, and then you are pushing it out. Now that pushing out, that what you're getting out, that's your main money maker, so to say. Basically that is what's providing your thrust. That is what your action is. Let's say 100 cubic meters of air per second pushing out of your engine, and then that's pushing your plane backwards. So that's the reality of it. You're taking air, you are adding chemical energy into it, and then you are exhausting it. Now again, if you think compressor will consume energy if you have to do something like that, that will be absolutely true. So to get to spin the turbine itself, we use another turbine. That this turbine is on the exhaust flow. So let's say you produced 10 megawatts of energy here. The turbine will take 2 megawatts of that, feed that 2 megawatt into compressor, so it becomes a self-sustaining system. So basically once you start it, however you're gonna start, it's more like how you start with a petrol engine, with a small starter motor. Here there would be a small jet engine that would be started with another smaller starter motor. So you will have in planes, if you are familiar with, in a tail you will see always an exhaust port. That is for the what we call auxiliary power unit. So there is a small jet engine that can be started with a basically electric motor. They start that jet engine powers air compressor that is big enough, powerful enough that it can start these puppies. And once the engine number one, let's say all planes have generally 2 engines, once engine number 1 starts, it will start the second number. Is this because this turbine stage consumes lot of energy. If you want to burn liters and liters of fuel per second, your compressor has to do a lot of work. So that turbine gives that power, that 2 megawatt of power, and then you get 8 megawatt of thrust. So this is what you are having, that exhaust. The hotter it is, the faster it is, the more noisier it gets, but it also improves your thrust. That is why fighter jets are they actually make more noise than your jumbo jets, because they can go fast. They can go really, really fast. So that's the working of it. Now we have to understand the basic start. Point number one is axial compression. What does that axial means? It compresses air. Now it compresses it to a very ludicrous degree, because you might be familiar with this sort of equipment, leaf blower or something like. They are quote unquote compressed air, because they take air, they forcify it. Now again, it will barely go to 2x. Well, let's say 15 psi in, 30 psi out, and that's maximum. That's unlikely, but you get the idea. And even this puppy consumes a lot of power. This is what, 500 watts of rated power. So you can understand that if you're talking about these puppy, it will consume power. So what we are gonna achieve in jet engine is basically up to 44 to 1. So basically multiply 15 psi of sea level air versus 44. That's what kind of output you are getting from this kind of compressor. Now this compressor has an airflow, same as every compressor, but if you are familiar with your car air compressor, it will be like tuk, 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 piston. It's not very efficient. Now this axial systems are much more efficient, again requires much more airflow to it. Basically it's not good for small scale. So you have a rotation system. Now if you're familiar with jet engines, or have you seen it in many museums, you will see something like that. Now that's absolutely true, it's an actual engine, but problem is because they remove the chunk from it, they remove the stator. So you may think, okay, that's how it is, but there is always a static thing in between, and those static thing is what is guiding the air. So there is 2 parts to it, one rotor and another is stator. So the blades push the air in, but how do you make sure the air does not come out of it? Again, you are compressing in an open flow. Pistons have the advantage of valves blocking it. Basically you take air in and then you block it, it cannot go anywhere. Then you push it, then you let the compressed air go out. Here there is no ceiling like that. So how the heck you make sure while you're rotating, you're compressing air and the compressed air does not bounce back? So that is why if you see in Wikipedia, you will always see something like that, a crisscrossing. Now this crisscrossing is what we call basically blades and stators. Now these both of them work together to make sure that does not happen, that you compress the air bounces back. That does not happen, and it needs a lot of energy. I will keep coming back to that because this is very heavy. It was so heavy that for certain rocket basically jet engines, they gave up and they simply use the T-tap to ignite it. So axial compressor is the step one. Then we come to the combustion part. Basically, you have compressed air, you have the jet fuel. How the heck you gonna burn it? Now you may think, okay, burning it, I have a lot of oxygen, I am gonna burn it. Now think of it this way: if you have a candle, burn it and blow on it. You take it out. Now, if you are old like me, you must have been familiar with, especially in India, kerosene lamps. Again, they have a paper wick. I'm saying cotton wick, and it's a thick thing. Now again, blowing it and blowing it out is hard. But again, if you use your leaf blower to blow it out, it's quite easy. Same goes for uh, this puppy also, because the amount of air is so high, you can easily put it out. Like it's traveling at like 500 feet per second. You can easily blow out any kind of temperature. It's like you put blow torches. So how the heck you make sure it even burns in the first place? Now what we do is to stabilize the airflow. Basically, air is very high speed. We are like, okay, chill bro, chill. How the heck you chill it? You basically make it fight against itself. So this is a what we call combustion chamber. So you take the air, you split it. Now you never actually burn 100% of the air, because A, you cannot do that because there is nitrogen in it, and B, that will melt everything. So you take, let's say, 25% of air, you let that into the central system. Now here you will have fuel injection, and fuel injection will mix that air, and then you will ignite it with a spark plug. Now here's the deal: if the engine is running basically in altitude, traveling at 700 km per hour, yeah, this process will not be stable. It will simply blow out. The moment you ignite it again, you will have boop, boop, boop. It will not run continuously, which you want. So what happens here is basically you see a lot of small holes. So that 75% of air that you bypassed, you make them come inside. Now you make them come inside at the opposite angle. So basically your fuel injector and air is coming like this. You make the bleed air coming like this from this side. You are making them collide here. Now where you collide, you create a vortex, you create a basically turbulent air. Now the benefit of turbulent air, it mixes very well. So it also atomizes the fuel. Basically, burning liquid fuel is not efficient. You want it to be atomized, basically as close to spray as possible. So that's what's happening. Basically, you are creating a reverse flow from that 75% air, and you are encompassing the incoming fuel plus air, and you ignite it. Now that place creates a turbulent region. That turbulent region is stable. So no matter how fast your compressor blows the air in, or how fast your total system is moving, that air, like that small zone, is becoming like a safe haven for flame. So flame will keep continuously running there as long as it's not put out, because once it's put out, igniting is very difficult. But if you ignite your engine in at the beginning, it will work properly. And that happens like many older planes, even modern ones, have this issue. If they ever have, for some reason, let's say bad fuel, bad injector, or something bad happened, or basically the burner stopped working, they have to drop the altitude, because at high altitude they do not have enough oomph to start it again. So they have to drop it down, and again if engines are not working, the speed will automatically drop. So at the lower altitude and thick atmosphere, they can ignite it again. So you can understand that just making sure the fuel burns is very difficult. And everything, like your whole efficiency, happens here, because the better your fuel burning, the better mileage you're gonna get. Same as like how cars went from carburetor to fuel injector, same happened here. And when I'm talking about fuel injection here, it's on a different level. It's like pumping swimming pool worth of fuel in 1 second. So it's very different. Now this has a lot of ratios to do with it. You never burn 100%. The sole reason is that even if you have a metal that is like very good, most metal will lose structural integrity if they ever are exposed to 1000 degrees Celsius. Now you might be like, hey, metal melts at like 1500. I'm talking about structural integrity. Let's say this is a steel beam, and it's like this will melt at 1500 degrees Celsius. Okay, awesome. But what will happen if you heat it up to 600 degrees Celsius? Nothing. You put weight on it, it's like that happened. That's why we make metal red hot in order to work on it. We don't melt it to work on it. We call it work heating, so to say. So same will happen here. Now again, in this scenario, you are talking about as high as 2000 degrees Celsius continuously. So if your flight is like 20-hour long, you're talking 20 hours of 2000 degrees. Nothing on this planet can withstand that. So that is why that air turbulent mixture is so critical, because it's done in such a way that flame never touches anything. It's like in mid-air, the flame is in mid-air. Even though fuel injector is pumping fuel, it's not igniting because it's not atomized. So it gets atomized in a turbulent region. The igniter ignites it in the turbulent region, and it's encompassed by the 75% air that you never burned. So it's completely stable. Basically, it's a magic. It's almost like the flame is flying here and nothing else is touching. Now there is another reason for that. Again, I specified the temperature is too damn hot. If you really burn it to its maximum capacity, and you're gonna melt through the turbine, that's gonna rotate the main compressor. So how the heck you make sure You don't. Basically that 75% air is for that reason only, so it drops the temperature. So fuel air burnt, you got the temperature, you got it to 2000. But what happens if you dump lot of unburnt air without any chemical energy into that? You drop the temperature, so temperature now drops to 1500 or 1300 degrees Celsius. So this is the whole area. So designing this puppy, basically where it works from sea level to high altitude, it's very difficult. Now engineering these puppies are on a different whole scale. Like you can have the same everything, basically same compressor, same turbine, but if you change your combustion system, and if combustion is much more efficient, your stock prices will go up. So it's a completely different thing. Whole efficiency, whole your mileage, whole how much oomph you can get out of it. Because again, even if let's say your turbine is magic material, it's never gonna melt. If you can't burn hundreds of liters of fuel per second, you're not gonna get too much oomph out of it. So this is why it's so complicated, jet engines. Now we come to the main workhorse of the jet engine. So far everything is simple. You have a compressor, you somehow manage to set fire to it. You got a lot of chemical energy, so your now exhaust velocity is much higher and temperature is much higher. Your now your engine is making noise, so everything is fine. But here's the deal: it's not gonna run the compressor forever. It's like running your car on a starter motor. So somehow you have to run the compressor itself. So you utilize turbine. Again, nothing on this planet can handle that kind of temperature. So what do? Basically, first you cool down the temperature. You never put 2000 degrees Celsius to it because it's gonna melt flat out. So first you cool down by mixing unburnt air. Then you do something very interesting. You put cooling holes on your puppy. So basically, how the heck you cool it? That's closely guarded secret. So the company might say, oh, we have air cooling. Oh, might have liquid cooling, or we might have this or that. But they're never gonna specify how exactly they are doing it. Because if let's say Pratt & Whitney and Rolls-Royce are competing against each other, and one of them figures out how the heck, let's say they increase the temperature by 50 degrees Celsius by improving a cooling method, they get 50 degrees Celsius more. That translates to a lot. Like they will literally remove the other component from market, because the fuel mileage from the another one would be much higher. So that is why. So blade like fuel is 2000, blade is 1500, generally below than that, or you can go as high as 1700 degrees Celsius. So that is the main game. We want these puppy as strong as possible. Now but again, how the heck you design something that withstands 2000 degrees Celsius kind of quote unquote exhaust while at Mach 3? Because at this point you have dumped chemical energy into it. So it's a lot of hot gases. Basically it will erode through stone. If you put stone there, like a raw stone, it will cut through it, because blowtorch got nothing on this puppy. So you have to design basically something that can withstand a continuous 20 30 hours of blowtorch use every day till it's retired. So it is very difficult. Basically how much oomph you can get out of this is limited by this. So after you put the fuel, or even if you put rocket fuel into it, let's say you just dump, instead of dumping hydrocarbon, you're dumping raw liquid hydrogen, and you get a lot of oomph out of it. Again, if this puppy cannot turn that energy into compression, so you will have a self-sustaining system, your engine will stall. So this is the main deal. This is what takes 200 hours of engineering just to model one of them. So this is the limitations act. This turbine part. So this was my presentation about jet engine. As so far I have covered all the basics of it, and I'm reasonably sure you must have gotten some idea what the heck jet engines are. And I'm gonna make a more detailed video about ramjet, scramjet, and talk about nozzles and all that jazz. So you will understand much more about it. But I hope so far this introduction was helpful for you. You have learned something about it, at least got some idea about it. In that scenario, I would urge you to press like, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.